Greetings to you all. My name is Siwe Shokoketsi and I'm here with my fellow colleagues, Ms. Njangase, Mr. Ramitla, Ms. Mboto, Mr. Sitole, and Ms. Sater. Today we'll be presenting about electrochemical aptasensing detection of cadmium ion on a carbon black gold nano-platform. Cadmium is a highly toxic heavy metal that often comes from industrial waste. It contaminates water system and accumulates in the human body, especially in kidney, liver, and lung. Unlike other metals, the body cannot remove cadmium effectively, so even small amount can build up over time. This bioaccumulation can lead to serious health problems such as kidney failure, cancer, high blood pressure, and a condition called Itai disease. Because of its toxicity, the World Health Organization has set maximum safe limits of cadmium in drinking water to be just 3 parts per billion, and in South Africa the limit is 5 parts per billion. Traditional detection methods such as ICP and 2OES and atomic absorption spectroscopy are accurate but expensive. They require specific operators and are not portable. Electrochemical sensors provide cheaper, faster, and portable alternatives, and by using aptamers, which is a short DNA strand that can bind specifically to cadmium ions, we can make these sensors highly selective and sensitive.
To provide clarity and direction for our discussion, I will now outline the aims and objectives for the study. The primary aim is to develop a highly sensitive and a selective electrochemical aptasensor for detecting cadmium ions in water samples using a novel carbon black and gold nanoparticles modified screen-printed carbon electrode. The objectives are as follows. Firstly, we have nano-platform preparation. To prepare the nano-platform by drop casting carbon black and electrodepositing gold nanoparticles on the SPCE. This involves cycling the potential from -400 to 110 MV. Secondly, we have optimization. To optimize the conditions for aptasensor, including the incubation time and aptamer concentration, which were determined to be 30 minutes and 2 micro concentration, respectively. Thirdly, we have detection range and sensitivity. To achieve a linear detection range for cadmium from 1 to 50 parts per billion with a limit of detection of 0.14 parts per billion using a square wave voltammetry. Last but not least, we have application in real samples. To validate the aptasensor's performance by applying it to real water sample analysis and comparing the results with those obtained from inductively coupled plasma optimal emission spectroscopy. By achieving these aims and objectives, the study contributes to the development of efficient and reliable methods for monitoring cadmium pollution in environmental water sources.
I'll briefly explain the methodology of the research. The researchers have aimed to build a simple and sensitive sensor to detect cadmium in water. First, they prepared the base electrode, which was a screen-printed carbon electrode. They improved it by adding carbon black to increase the conductivity and porosity, and then deposited gold nanoparticles on top. Next, they attached a DNA aptamer to the gold surface. The aptamer was specifically designed to recognize the cadmium ions. For detection, water samples containing cadmium were placed on the electrode. When cadmium bound to the aptamer, the DNA strand folded and allowed more current flow. The change was measured using a square wave voltammetry. Finally, the sensor was tested for performance. It was checked for sensitivity, stability, and selectivity against other material and metals. The team also tested it on real water samples like tap water and industrial water waste. Thank you.
Under results and discussion, we first have physiochemical characterization, which shows the FESM images of the bare and modified electrons. The round-shaped particles shown on figure A and B are similar, which suggests that the carbon ink in the SPCE and the synthesized carbon black have similar structures. However, figure B shows more porous holes compared to A, likely due to the extra layer of carbon black that was added. Figure C shows small bright round spots. These are nano-gold particles, which shows that the gold was successfully deposited. And furthermore, the EDX spectra was further used to confirm the deposition of the gold, as you can see on figure D. Secondly, we have the optimization of experimental parameters. To achieve high sensitivity in detecting cadmium, key experimental parameters including aptamer concentration and incubation time were optimized. In figure A, SWUV was used to optimize aptamer concentration and incubation time for cadmium detection, where the current response increased while aptamer concentration reached a maximum of 2 micromolar, after which it decreased due to the overcrowding on the electrode surface. On figure B, it shows the peak currency that increased up to 30 minutes, as you can see on figure B, then slightly decreased beyond that. Therefore, the 30 minutes was chosen as the optimal incubation time. In figure C, it shows the SWUV response of different modified electrons tested with 10 ppb cadmium D. The SPCE CBAUM sensor, which is the one in black, gave the highest currency and better reproducibility compared to others, demonstrating the synergetic effect of carbon black and gold nanoparticles, improving aptamer incubation and
Just to add on what Ms. Mbot was just saying, we used the square wave voltammeter to assess the changes in the Faraday currents on the electrode where we vary the concentration of the aptamer. We found that when we increase the concentration of the aptamer, the reading of the current increases. The reading of the current increases. However, there is an extent to which we can increase the concentration of the aptamer until the reading starts to decline, as shown in the graph. This is due to the density of the aptamer in the solution, which causes more repulsive forces between the aptamer and the ferrocyanide redox probe. Hence, the reading starts to decline due to those repulsive forces. On another experiment, we've investigated how the electroactive surface area on the electrode affects the reading of the current. According to Regel's self-seek equation, the higher the electroactive surface area on the electrode is the higher the current being induced. Is the more current is being induced. So SPCE and carbon black and gold nanoparticles all have their individual electroactive surface area. So when we put them together, when we bring them together, we achieved a more bigger size in the electroactive surface area on the electrode. Hence it induces more current than any other modification can. And then on other experiments, we investigated how the different modification on the SPCE affects the sensitivity and the conductivity or the induction of current on the electrode. We used SPCE, bare SPCE, or unmodified SPCE as a control factor and a point of reference. We then modified that SPCE with carbon black, and we found out that the current induced increases by 11% with reference to bare SPCE or compared to bare SPCE. We then modified the SPCE with gold nanoparticles, and the results increased by, or the current increased by 50% with reference to bare SPCE. We then combined carbon black and gold nanoparticles on the SPCE. We modified them both on the SPCE, and then the results or the current induced increased by 80%. This is due to the cooperation of carbon black and gold nanoparticles in fusiling or transporting the electrons to the ferrocyanide redox probe. We then modified SPCE with both gold nanoparticles, carbon black, and added an aptameter. And then this resulted in a lesser reading than we have expected, because this is due to, again, the repulsive forces between the aptamer and the probe.
Conclusion: the modified SPCE with CB aims and an aptasensing was developed to detect cadmium ions in water. It uses a DNA aptamer that has affinity and binds this cadmium ion. So the sensor works effectively in comparison with the bare SPCE or the SPCE with CB. Okay, the sensor detecting very small amounts of cadmium as low as 0.14 parts per billion in a range of 1 to 50 parts per billion showed a good accuracy, stability, and high Faraday current sensitivity. This method would have been the most effective if the repulsive forces between the aptamer and the ferrocyanide redox probe did not affect the fusiling of electrons. The method uses the aptamer's ability to specifically bind to cadmium, avoiding issues other methods face like interference from other metals. Overall, it offers a simple and effective way to detect cadmium in water. Acknowledgement: we want to thank T. Fakude for investigation methodology, writing the original draft and writing the review and also editing. Then we would like to thank A. Arotiba for conceptualization, methodology, supervision, resources, then writing the review and editing. Then N. Mabuva for conceptualization, funding, and project administration, resources, supervision, writing